Hello, my dear, and let's start our lecture number 13 on course of avionics engineering. Okay, so today's lecture called GPS or Global Positioning System. You know, GPS is basically a radio navigation system which derives the user's position from the radio signal transmitting from a number of orbiting satellites. The fundamental difference between GPS and earlier radio navigation systems, such as LORAN-C, by the way, it's not now longer in use, is simply the geometry of propagation from ground-based transmitters compared with space-borne transmitters. An orbiting satellite transmitter can provide line-of-sight propagation over the vast areas of the board. And this avoids the inevitable trade-offs of less accuracy for greater range, which are inherent with systems using ground-based transmitters. The satellite signal also penetrates the ionosphere rather than being reflected by it, and so that the difficulties encountered with sky waves are avoided. GPS provides a superior navigation capability to all previous radio navigation systems. For this reason and space constraints, coverage to radio navigation system has been confined to GPS. Satellite navigation can be said to have started with the successful launching by the Soviet of the world's first orbiting satellite, Sputnik 1, in October 1957. The development of the first satellite navigation system, Transit 1, was triggered by observations made on the radio signal transmitted from Sputnik 1 and was initiated at the end of the 1958. Transit 1 resulted in a worldwide navigation system which has been in continuous operation since 1964. GPS started as a series of preliminary system concept studies and system design studies in the late 1960s. A phase 1 is concept and validation program was carried out from 1973 to 1979 and followed by the phase 2 full-scale development and system test program from 1979 to 1985. The next, phase 3, production and deployment program, was initiated in 1985. 12 development satellites were used to develop and prove the system, and the first production satellite was launched in February 1989. Some delay to the program was incurred by the Space Shuttle Challenger disaster in 1986. As it had been originally intended to insert all the production standard GPS satellites into orbit using the Space Shuttle. A Delta II launch vehicle was used subsequently, and deployment of the 24 production standard GPS satellites was completed in the late 1990. A very similar satellite navigation system called GLONASS has been developed by the Russians. Although designed for military applications like GPS, it is available, but it has not been used elsewhere at the present time. Now, it's maybe counted from 2010 and until now. Let's start. Next subtopic today's lecture, GPS system description. The overall GPS system comprises three segments, namely the space segment, the control segment, and the user segment, and is shown schematically in the next slide. The three segments are briefly summarized, will be summarized in our lecture. So let's start with the space segment. This comprises 24 GPS satellites placed in 6 orbital planes at 55 degrees to the equator in geosynchronous orbit. It's up at 20,000 kilometers above the Earth. The orbit tracks over the Earth, forming an egg beater type pattern. 21 satellites are required for full worldwide coverage, and 3 satellites act as orbiting power. Okay? The GPS satellite use 2 frequency transmissions, L1 at 1571 MHz and L2 at 1227 MHz for transmitting the digitally encoded navigation message data at 50 Hz modulation on both the L1 and L2 channel. No matter. The navigation message data will be explained in more detail in a bit later in our today's lecture. But basically comprises the satellite orbital position parameters, clock correction parameters, and health information for itself, and the other satellite, and the almanac data for all the satellites. Spread spectrum techniques are used to both the L1 and L2 frequency channels. The L1 is modulated by 1000 MHz clock rate, pseudo-random code known as the course acquisition code. A different course acquisition, or simply CA code, is assigned to each satellite. A quadrature carrier component of the L1 signal is modulated by precise code, which uses 10 times the clock rate of the CA code. CA, as you remember already, course acquisition code. The L2 transmission is modulated by the P code only and enables correction to be made for ionosphere delay and quantity. The dual frequency transmission enabling this correction to be derived. But it should be noted that until recently, the GPS accuracy available to civil users was deliberately degraded 50, sometimes up to 100 meters. The poor accuracy of 16 meters could only be obtained by military users with access to the P code on the L2 transmission, which was encrypted. And this restriction was removed only in millennium, more than 25 years ago. Today we have a quality 2 times higher, up to 8 meters. Next, control segment. And this comprises a master control station at Colorado Springs in USA, and 5 monitor stations located worldwide. The control segment is operated by the United States Department of Defense, DoD, in short. The control segment tracks the satellite and predicts their future orbital position data and the required satellite clock correction parameter, and moreover, and update each satellite on the uplink as it goes overhead. The GPS full system accuracy is only available when the operational control system is functioning properly, and navigation messages are uploaded on daily basis. So, the GPS satellites are, however, designed to function with the control system inoperable for a period of 800 days with gradually degraded accuracy. And this gives the GPS system a high degree of robustness. Now, let's come to the user segment. The user segment equipment, as mentioned a bit earlier, is entirely passive and comprises a GPS receiver. A very wide variety of compact, lightweight, and inexpensive GPS receivers are now available, all using the same basic concept. The user concept operation is very briefly enacted. The operator first enters the estimated present position and the time. The GPS receiver then starts to search for and track satellites. The data coming in identifies the satellite numbers, locates the satellite in space, and establishes the system time. As will be explained in our next module today, the GPS receiver needs to track the signal from at least 4 satellites to determine the user's position. As mentioned in the introduction to this module, the user's 3D position is determined to an accuracy of 16 meters as before. Yes? And more widely now, so the 8 meters RMS, 3D velocity to 0.1 meters per second, or 10 centimeters per second, RMS by measuring the Doppler shift, and time to be seen 100 nanoseconds for 1 sigma. Now, let's start another subtopic today's lecture, basic principles of GPS. Nevertheless, many of your today widely used GPS system and coordinate, but I am trying to repeat, wrap out your knowledge about it, okay? So, the basic principle of position determination using the GPS system is to measure the spherical ranges of the user from a minimum of 4 GPS satellites. The orbital position of this satellite relative to the Earth are known to extremely high accuracy, and each satellite transmits its orbital position data. So each satellite transmits a signal which is modulated with the CA pseudo-random code in a manner which allows to the time of transmission to be recovered. Okay? The spherical range of the user from the individual transmitting satellite can be determined by measuring the time delay for the satellite transmission to reach the user. Multiplying the time delay by the velocity of light then gives the spherical range R of the user from the transmitting satellite. The user's position can lies on the surface of the sphere of radio, as shown in this slide. The system depends on precise time measurement and requires atomic clock reference standard. The need for extremely high accuracy is the time measurement can be seen from the fact that at 10 nanoseconds, or what it means, it's 10 in power minus 8 seconds, time error results in a distance error of 3 meters. At the velocity of light, 3 times 10 in power 8 meters per second. I hope you remember this, okay? So, each GPS satellite carries an atomic clock which provides the time reference for the satellite data transmission. Assume for the moment that this time is perfect. The correction required will be explained shortly. Given a perfect time, a reference in the used equipment, measurement of the spherical ranges of 3 satellites would be sufficient to determine the user's position. The user's equipment, however, has a crystal clock time reference, which introduces a time bias in the measurement of the transit time of the satellite transmission. The first component is the transit time of the ranging signal, and the second component is the time offset between the transmitter clock and the receiver clock due to the non-synchronization of the clocks. Measuring the spherical ranges from 4 satellites, as shown in this slide, enables the user's position to be determined and yield 4 equations containing the 4 unknowns, with the 3 position coordinates of the user and the time bias in the user clock. Are you agree with me? Nice. Let's go. The position coordinate of the user can thus be determined together with very accurate time information. And figure on this slide shows the data transmission waveforms and illustrates the user time bias delta t. Delta t, user time bias from the system time. And the time delay, delta t1, delta t2, delta t3, and delta t4 for the signal transmitted from the satellites to reach the user. Okay? For pseudo ranges R1P, R2P, R3P, and R4P to the 4 satellites S1, S2, S3, and S4. So we can get these 4 equations. Now, let the range equivalent of the user's clock offset be T. So we may write T equals C times delta T. And hence, from basic 3D coordinate geometry, we can get these 4 equivalent equations for R1, R2, R3, and R4. Generally, in the final, we can see it's very, very simple. Here, R1, R2, R3, and R4 are the actual ranges from the user's position to the 4 satellites. And the coordinate of the satellite x1, x2, x4, xyz for any 4 positions, respectively. Okay, so these 4 equations with 4 unknowns can start be solved as you know from basic of math from the first year study, and yield the user's position coordinate x, y, z, and user time offset delta t. So the assumption of perfect satellite clock made initially in the discussion, however, is not a valid one. And in fact, the clocks are slowly but steadily drifting away from each other. The satellite clocks are therefore mathematically synchronized to a defined GPS master time, which is maintained at the master control station. This GPS master time is continuously monitored and related to the United Time Coordinate, UTC, Universal Time Coordinate, UTC, maintained by the United States Naval Observatory. Its satellite time is related to GPS time by a mathematical expression, and the user corrects the satellite time to the GPS time using the equation, as you can see on the left top corner of this slide. T proportional T subscript C over S minus delta T. So T here is the GPS time in seconds. Next component, T sub C over S over C, is the effective satellite time and signal transmission in seconds. And the third component, delta T over S, is the time offset between the satellite and GPS master time. The time offset here, it might be computed from the following equation, as you can see here. Here the coefficients are not R1, A1, A2, are polynomial coefficients representing the phase offset, usually frequency offset and aging term of the satellite clock with respect to the GPS master time. And as you can see, we have last component, delta T sub R, is a relativistic term measured in seconds. Parameter T is the GPS time, and the TOC is the epoch time, at which the polynomial coefficients are referenced, and generally TOC are estimated by the control segment for each satellite clock and periodically uplinked to the satellite. So these coefficients are transmitted together with the satellite orbital position data, termed the ephemeris parameter, to the navigation user equipment as navigation messages. The clock correction for the 4 satellites are designated as the tau, tau1, tau2, tau3, and so on. So the spherical ranges R1, R2, and R3, and R4 are thus given by these 4 equations. And so here you can see that they're the same all 4 corrections for the tau. So all satellite clocks are mathematically synchronized to the GPS master time by means of these clock correction terms. The error in synchronization will grow, however, if the polynomial coefficients are not, A0, A1, and A2 are not updated periodically. The navigation user requires the ephemeris parameters, that is the instantaneous position data of the GPS satellite, which are being used for range measurement, as well as the clock parameters in order to compute the user's position. You know, the ephemeris parameter defining the satellite orbit position data with respect to Earth's reference axis and comprise 16 parameters in all. And figure on this slide illustrates the satellite Earth geometry and the definition of the orbit parameter. The control segment processes the tracking data acquired from the monitor station to generate the orbit estimates for the GPS satellite. The predicted estimates of the satellite position coordinates are generated by integrating the equation of the motion of the GPS satellite. These Cartesian position coordinates are then fitted mathematically over a specified interval of time to compute the ephemeris parameter. Both clock and ephemeris parameters are downlinked to the user at 50 beats per second data rate, modulated in both CA and P code, sometimes called as Y code navigation signal. The navigation message uses a basic format consisting of 1500 bit long frame and made up of 5 subframes, each subframe being 300 bits long. Subframes 4 and 5 are subcommuted 25 times each, so that a complete data message takes a transmission of 25 full frames. Subframe 1 contains the clock parameter, and subframes 2 and 3 the ephemeris parameters for the satellite. Subframes 1, 2, and 3 are repeated every 30 seconds, so that it is possible for the user to update the clock and ephemeris parameters every 30 seconds, right? Subframes 4 and 5 have each 25 pages, so that these subframes are repeated only once in 12.5 minutes. In addition to ephemeris and clock parameters of the satellite, each satellite transmits almanac data of all satellites to the user. This is primarily to facilitate satellite acquisition and to compute what is known as the geometric delusion of precision. Geometric delusion of precision. This value to assist the selection of the satellite to achieve better accuracy. The optimum geometry occurs when one satellite is at the user's zenith, so directly overhead, and at least 3 other satellites are evenly spaced around the user's horizon. So conversely, a large error would occur if the satellites were clustered together, so that their lines of sight tended towards being as a parallel. And health data for all satellites is also transmitted. The almanac data and satellite health data are contained in subframe 4 and 5. Ionospheric data for a single frequency user and the conversion parameters for GPS time to UTC are contained in subframe number 4. Okay? So the navigation equations are basically nonlinear, as can be seen in these other 4 equations, but can be linearized about nominal value for their solution by applying Taylor series approximation. Okay, so generally we can resolve this equation. And let's start another subtopic today's lecture: solution of navigation equation. So let's have as x sub u, y sub u, and z sub u denote the nominal a priori best estimate values of the user's coordinate x, y, z, and clock offset range equivalent t. Okay, so let delta x, delta y, delta z, and delta t denote the correction which need to be to these nominal values. So we have this expression on the first slide. The actual range from the some satellite from 1 to any other number is given by the second equation you can see here. Here the x sub y sub I and z sub I are the position coordinates of the satellite, I satellite. Applying Taylor's series expansion about the nominal values, we can approximately get this expression for r sub I. Here we have this coefficient x for x, y, and z, evaluated for x, u, yu, and z. So, partially differential equation with respect to x get us this expression on the bottom. And here we have this coefficient xix, hiy, and hiz. And the same r sub iu. You can this as generally as a square root from this expression. So here r sub I we can get from the previous equation plus h for any three coefficients x, y, and z. Okay, and the range error of this I satellite, in our case it's delta alpha I, may be given by this simple expression. And when substituting as a t equals tu plus delta t, we can get this final equation at the right bottom place of this slide. And here we have next matrix equation. Delta R on the left equals x coefficients times the matrix for delta x, y, z, and delta t. And this linear matrix equation is solved to yield these all four components: delta x, y, z, and delta t. And these values are used to correct the nominal value to the user's position, and certainly and the clock offset too. The process is repeated until this matrix, column matrix, become negligible. But it should be noted that the measurement uncertainties and errors have been left out of the equation at this stage for simplicity. Okay? A sequential processing of the measurement is used in dynamic user application because better estimate can be obtained by utilizing the previous estimate and their associated uncertainties. In this case, we're using Kalman filters. Kalman filters are often used now. The matrix of the partial derivatives for h, 1x, y, and z is generally referred to as the H matrix. But you should be noted that all these H coefficients are the direction cosine of the AI satellite range vector. And so the H matrix can be used to access the geometric dilution in all precision. Okay? Now, so as you can see, generally very simple. You no need to calculate as many years ago when I was in your age for the beginning as a pilot. Yes, we use the navigation ruler, but today it's more simple. Next subtopic today's lecture: integration of GPS and INF. GPS and INF are wholly complementary, and their information can be combined to the mutual benefit of both systems. For example, calibration and correction of INF error. In this case, the GPS enables very accurate calibration and correction of the INF error in flight by means of, namely, Kalman filter. The INS can smooth out the step change in the GPS position output, which can occur when switching to another satellite because, because of the change in inherent error. And jamming resistant like any radio system. GPS can jam, albeit over a local area, but also it can be given a high degree of resistance to jamming. The INS, having had its error previously corrected by the Kalman filter, and is able to provide accurate navigation information when the aircraft is flying over areas subjected to severe jamming. Antenna obscuration. GPS is a line of sight system, and it is possible for the GPS antenna to be obstructed by the terrain or aircraft structure during maneuver. And finally, antenna location correction. In this case, the GPS-derived position is valid at the antenna and needs to be corrected for reference to the INS location. The INS provides attitude information, which, together with the level R constant, enables this correction to be made. Okay? So, let's start another subtopic. Differential GPS. As explained in the preceding module, the horizontal position accuracy available to all GPS users, as civil as military, and is now 6 meters. And this wasn't the case, however, until millennium, where the restriction of selective availability was removed. Concern about potential enemies using GPS to deliver missiles and other weapons against the, say, US can lead to a policy of accuracy denial, and generally known as selective availability. The GPS ground stations deliberately introduced satellite timing error to reduce the positioning accuracy available to civil users to a horizontal positioning accuracy as 100 meters to a 95 probability level. And this was deemed adequate for general navigation use. But in practice, it did not satisfy the accuracy or integrity requirement for land or hydrographic survey, coastal navigation, or airborne navigation too. It should be noted that even the 6 meters accuracy now available is insufficiently accurate for many applications. For example, positioning of offshore oil drilling rigs or automatic landing in the case of airborne application. And 6 meters, especially per second vertical voids, may be very high. Okay? A supplementary navigation method, known as differential GPS, is therefore being developed to improve the positioning accuracy for the growing number of civil applications. Differential GPS can be defined as the positioning of a mobile station in real time by correcting and certainly possibly Doppler or phase mode. So GPS self the range. The corrections are determined at a static reference station and transmitted to the mobile station. A monitor station may be part of the system as a quality check on the reference station transmission. The success of differential GPS can be seen from its application to new markets, such as locating land vehicles used by the emergency services Successful trials for automatic landing and taxiway guidance have also been conducted. It is now widely used in land and hydrographic surveying applications. Okay. Basic principles. The basic principle underlying differential GPS is the fact that the errors experienced by two receivers simultaneously tracking a satellite at two locations close to each other and will largely be common to both receivers. The basic differential GPS concept is illustrated in this slide. The position of the stationary GPS reference station is known to very high accuracy, and so that the satellite ranges can be very accurately determined, right? And knowing the satellite ephemeris data. The error in the pseudo range measurement can then be derived and the required correction computed and transmitted to the user's receiver over a radio link. The errors present in a GPS system are illustrated schematically in this slide. And now let's briefly describe it. So, GPS satellite clock. Let's start with name. GPS satellites are equipped with very accurate atomic clocks, and corrections are made via the ground station, as explained in the preceding model. Okay, I hope you remember. Even though very small timing errors are present and so contribute to the overall position uncertainty. Selective availability deliberately introduced noise equivalent to around 10 meters in the individual satellite clock signal. Next, satellite ephemeris error. Now, the satellite position is the starting point for all the position computation, so that errors in the ephemeris data directly affect the system accuracy. GPS satellites are injected into very high orbit and so are relatively free from the perturbing effects of the Earth's upper atmosphere, even though they still drift slightly from their predicted orbit and so contribute to the system error. Next component, atmospheric error. You know that radio waves slow down slightly from the speed of light in vacuum as they travel through the ionosphere and the Earth's atmosphere. And this is due respectively to the charged particles in the ionosphere and the water vapor and maybe neutral gases present in the troposphere. All these delays translate directly into position error. And the use of different frequencies in the L1 and L2 transmission enables a significant correction to be made for ionospheric delay. Generally, it should be appreciated that this facility was not available to civil users prior millennium, near the 20 years ago. A predicted correction factor for the Earth's atmosphere path is made in the receiver, but this is based on a statistical model, and there are inevitable residual errors present. Let's start with multipass error. Now, the GPS satellite signal is received by the direct line of sight, LOC path. But the signal may also be received as the result of reflection of local obstruction. The reflected signal arrives slightly delayed from the direct line of sight signal and the term multi-pass signal. Why? Because line of sight very direct and rest maybe from our wall and get. So the multi-pass error experienced in a moving receiver occur in a random fashion, which results in a noise like pseudo-range error. The problem is considerably alleviated by the use of an early late delay lock loop and suitable filtering technique. Next component, receiver clock. Internal noise in the GPS receiver clock introduces a small error. So, in our case, GPS enables most of the above errors to be counteracted, as they are common onto both the reference station receiver and the user receiver. The exceptions are the multi-pass and receiver errors, and these are strictly local phenomena. The dramatic improvement in accuracy effect by differential GPS can be seen from these tables. Separation distances between the ground reference station and the mobile user can be up to 300, even up to 500 kilometers, and separation of thousands of kilometers or beyond, and are not unknown. And this slide is a simplified functional diagram of a generic differential GPS system. Radio links can be released in one of a number of forms to provide a suitable narrowband communication channel to the mobile receiver. Dedicated radio channels within the MF, HF, VHF, or UHF bands are used. Frequency diversity and error checking codes are used to provide protection against data corruption caused by the vagaries of propagation. The satellite pseudo-range measurement in the user's GPS receiver is carried out by the correct correlation of the received satellite signal with the receiver-generated replica of the known satellite CA code using a code tracking loop. The accuracy of the time measurement by CA code tracking loop is inevitably ultimately limited by noise sources, such as multi-pass reception. You know, the ground reference system, reference GPS station in the differential GPS system uses these Doppler frequency shift measurements. Why? To improve the accuracy of the pseudo-range measurement. Integrating the Doppler shift over an inertial provides a measurement of the change in satellite to receiver range. The range itself cannot be measured because the integer number of carrier cycles usually not known. The information extracted from a carrier tracking loop can take the form of Doppler observation or a continuously integrated Doppler observation, more commonly called a carrier phase observation. And the multi-pass and noise-induced error found in the carrier phase observation are negligible compared to those on a CA code observation. The accuracy improvement is commensurate with the rates of the L1 code wavelength and carried wavelength like 290 meters and 0.19 meters respectively. And carrier phase filtering can be carried out using Kalman filtering technique. Next subtopic for today is future augmented satellite navigation system. The advent of satellite navigation systems and satellite communication links has provided new capabilities for aircraft precision navigation, particularly in civil operations. Providing the integrity and accuracy requirements can be met, and satellite navigation systems are able to support all phases of flight, including all weather precision approaches to airports not equipped with ILS or maybe MLS installation. In conjunction with satellite communication links, they can also prove the capability for remote air traffic control, as shown in this slide. Successful concept proving trials were, in fact, conducted by the UK Air Traffic Control Authorities in conjunction with British Airways around 1996. The trials used the onboard GPS receivers and SAT-COM radios in a British Airways Boeing 747 airliner to monitor the aircraft flight path on normal commercial flight to the West Indies. Detailed changes in the aircraft flight path over the West Indies were accurately monitored from the UK over 3,000 miles away. The potential for more flexible air traffic control systems can be seen, and it is only a matter of time before they are introduced. Some reservations exist as to whether the integrity of the present GPS system is sufficiently high to meet the navigation integrity requirements in safety-critical phases of the flight and adverse weather conditions. Okay? Also, the probability of GPS receivers producing erroneous position data is very low. And there have been recorded instances of erroneous GPS position data in flight. There have also been reservations about total reliance on GPS, as it is a military system, which is completely under the control of any military command. Well, like in my country, in Ukraine, where we have the war with Russian aggression. The accuracy available to civil users during the 1990s was also limited to 50 meters, twice less than 50, by the policy of selective availability, as already explained. And this was inadequate for precision approaches. An augmented satellite navigation system provided by additional satellites under international civil control was therefore proposed and studied in detail by the European civil authorities from the late 1990s. The additional range in signals and monitoring will enable the integrity requirements to be met and will also provide increased accuracy. The go-ahead for the new system, known as the Galileo system, was announced by the participating countries in the European Union in March 2002. The Galileo system will be interoperable with GPS from a user perspective and will comprise up to 40 orbiting satellites. The system will provide a positional accuracy of the order of 1 meter worldwide when it comes into operation. The Galileo satellite navigation system is scheduled to enter service around 2014. The development of differential GPS has enabled ground reference stations to monitor the quality of the satellite transmission. And they provide an additional check on the GPS system integrity for users within a 500 to even 1,000-mile radius of this station, and enable differential corrections to be transmitted to this user. Increased accuracy is obtained with errors in the few meters bracket, depending on the range from the ground station, as explained in the preceding model. Okay? A GPS satellite augmentation system is being developed in USA under the auspices of the FAA, called the Wide Area Augmentation System. The Wide Area Augmentation System, or in short, abbreviation WAAS system, is shown in this slide. And this will provide increased integrity by monitoring the GPS satellite transmission from a network of monitor ground stations, say US, and increase the system accuracy by transmitting the differential correction over communication satellite radio link. User position accuracy should be within 3 meters, enabling precision approaches to be accomplished in Cat 2 visibility conditions. Extensive trials of a wide area augmentation system, WAS evaluation system, have been conducted by the FAA over the last decade, and with very promising results. It appears very likely that the full system will be built and become operational over the next decade. Okay? I hope it's enough for today. Are you agree with me? Generally, I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.